Hey everybody. Today I want to take a minute and try to explain to you the idea of calculating equilibrium concentrations. So let's look at a particular problem here. In this particular problem, we want to consider the reaction of A going to 2B. And if we start with 1 molar A, and we know that Kc is 0.33, the question is, what are the concentrations of A and B at equilibrium? This is an ice table type problem. So the first thing we should do is write the Kc expression. And so you notice Kc is B squared over A. And that ultimately, of course, Kc is 0.33. So we've got 0.33 equals B squared over A. But we don't know what B and A are. So we're going to make an ice table. And you see our ice table here that lists our initial concentration of A as 1 molar. They didn't tell us an initial concentration of B, so that's 0. The good news there is we know that the reaction is going to have to at least initially proceed to the right. So we're going to lose some A and gain some B, but we still don't know what the equilibrium concentrations are. And we don't really have a good idea of what the change in concentration is. So what do? Well, what we do is put in for our change in concentration X, because we don't know it, okay? We don't have to worry about calculating Q here, because as I said initially, we know we don't have any products, so we know the reaction is going to proceed to the right. And when we put in our X for change, we do need to consider stoichiometry. So as you'll notice, the change for A is just X, or specifically minus X. But the change for B, 1, is going to be positive because we know the reaction is proceeding to the right. And 2, instead of X, it is 2X because for every 1A, there are 2 B's. So this gives us an expression where at equilibrium, for A, we have 1 minus X, and for B, we have 2X. We can plug these equilibrium values back into the Kc expression. So now we have 0.33 equals 2X squared, all squared on top, over 1 minus X on the bottom. We've got to solve for X. So how do we do that? Well, the first step in that process is probably multiplying both sides of the equation by 1 minus X. And if you do that, you get 0.33 times the quantity 1 minus X equals 4X squared. And you might say, well, why is it 4X squared all of a sudden? What we did is we squared the 2 and we squared the X from the top of our Kc expression. Now, we probably should distribute the 0.33. So we get on the left 0.33 minus 0.33x equals 4x squared. Those of you who have taken a bit of algebra might recognize this as an equation that could turn into a quadratic. If we add 0.33x to the right and the left side, and we subtract 0.33 from the left and the right, we get 4x squared plus 0.33x minus 0.33 equals 0. This is a quadratic equation. We need to solve for x. There's no easy way to simplify this expression and do that, so we're going to need the quadratic equation. And the quadratic equation is given here. It says x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. And it's worth pointing out here that in our example, that's a, that's b, and this is C. We're going to plug in those values. And when we do, we can solve the quadratic equation for x. Now, I'm not showing you all the steps here, but what I will show you is the answer. And you get two possible values for x, 0.249 and negative 0.331. Of course, negative concentrations are not possible, nor in this case would be a value of x larger than 1, because that would make our equilibrium concentrations negative. So we eliminate the negative 0.331, which means for our purposes, x is 0.249. We can take that value of x and return it to our ice table and plug it in. And if we do that, what we end up with as an equilibrium concentration of A is 0.751 molar and B is 0.498 molar. We can check if this is correct by taking those equilibrium values, plugging them back into the Kc expression, and solving for K. And if we do that, we get 0.33, which is the equilibrium constant we were given in the beginning. These are valid and correct solutions. It is worth noting that even though you may have different initial concentrations of A and B, and that therefore the equilibrium concentrations of A and B may be different, at the same temperature, K is a constant and will have the same value. This is probably the most complex of equilibrium problems you might see in this course. Do they get easier? Why is this one more complicated? Why did we have to use the quadratic equation? And is there a way to simplify the problem so that we wouldn't have to use the quadratic equation? And if so, how would we know? To understand that idea, let's back up a moment. Let's go back to the very beginning. Okay? Sorry, I went one slide too far there. Here we go. You'll notice here that the reason we ultimately end up with a quadratic equation is because of that x. If we didn't have 1 minus x as the concentration per A, we'd never end up with a quadratic equation and things would be simple. It turns out that we don't always have to keep that x. In other words, there is an approximation we can make if x is small enough. Well, how do we know if x is small enough? Well, the real answer is if you take the value of x, which we got, you recall, 0.249, and divide it by the initial concentration of that reactant, which is 1, and multiply that by 100. In our case, that comes out to 24.9%. If this value is less than 5, you can ignore that x for the reactant. Unfortunately, as you can see in this case, we couldn't do that because our value is 24.9. Now you might be saying, wait a minute, that doesn't help me because I didn't know what x was until I did the whole problem. And you're absolutely right. So how do we know this without going through all the work first? A good estimation of when you can ignore that x for the reactant can be found by taking the initial concentration, the initial concentration, 1.00 in our case, and dividing it by the value of K. In our case, that comes out to be 3.03. If that number, when you take the initial concentration divided by K, is greater than or equal to 1,000, you can probably ignore the x. You should check if you ignore x and solve the problem. You should check at the end to make sure that your assumption was valid by making sure that you get less than 5% here. If you don't, you'll have to go back, put x in, and probably use the quadratic equation. Hopefully this sheds a little bit of light on calculating equilibrium concentrations, and when we have to use the more complicated and time-consuming quadratic version versus when we do not. Ultimately here, there's not a substitute for a lot of practice to become comfortable with this process. Hopefully this video helped you along.